Hello and welcome to a presentation on neoclassical physics. Here we explain all physical phenomena, including quantum and relativistic processes in classical terms, with a little modification. This is the closest thing to the grand unified theory as of now. Neophysics has the most accurate theories of physics. We challenge you to disprove us. If not, we welcome you to join us in the revolution. In this presentation, we make a few general observations about the Riemann Zeta series and its supposed zeros. This series is deemed to be important in quantum field theory to get rid of the infinities occurring in some calculations. Let us begin with the harmonic series, that is 1 plus 1 by 2 plus 1 by 3 up to n terms. For this series, we can verify that the sum up to n terms is equal to natural log of n plus some constant for n much larger than 1. The harmonic series diverges as it depends on n, that is natural log of n, while the alternate harmonic series converges, that is we get 1 minus 1 by 2 plus 1 by 3 up to infinite terms is natural log of 2. It is very easy to verify this. We can write the alternating sequence up to 2n terms, that is write this out, and we can write this series as a sum of two finite series, this and this. Here there are 2n terms and here there are only even terms, and so there are n terms here, and here we negating all even terms twice here, multiplied by 2, so it becomes 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, giving back this series. So we can split this series into these two finite series. Now in this place we know the summation of the first n terms or 2n terms, so we can use those results, harmonic series sums here. So 1 plus up to 2n terms is natural log of 2n, up to n terms is natural log of n plus some constant here. So plugging these values in this series, we get the difference as natural log 2n minus natural log of n, which is just natural log of 2. So the alternating series has a sum which is convergent, natural log of 2. The harmonic series summation is only slightly off from the integral form equation. In the power series also, similarly we get the integral form summation, that is the series 1 plus 1 by 2 power a plus 1 by 3 power a up to n terms is closely approximated by integral of 1 by n power a. We know the integral of 1 by n power a is equal to n power 1 minus a divided by 1 minus a. So in this sum, what we get is, this is the major term and there will be a small residue. So we can note that this form does not work exactly at a equals 1, but as a tends to 1, a tends to the limit 1, then we get this expression. This reduces to log of n. And for a less than 1, we can see that this sum diverges, and for a greater than 1, this will be converging to a particular value given by this f of a. We can call this series as a function, zeta function, with n terms and each term raised to the power a. So we can plot the residue function f of a as this black line. So f of a is nothing but the difference between the series summation and the integral form. So the difference between these two terms. So red line is nothing but the data fitting to the black line. So what we find in the black line is that at a equals 0 it is 1, and at a equals 1 it has 0.5772, the same constant that we discussed earlier, and it has a minima at 0.24, which is, it reaches a minimum of 0.523. It rapidly drops and slowly rises. So basically what we see from this graph is this expression, this function zeta of a comma n is limited between these two terms, which is basically this is the integral form. So it is limited by this, approximated by this integral form equation. Now we can generalize this real number a in the zeta function as a complex number. So from the textbooks, we see that most of the time it is defined as an infinite series. So this is the zeta series. Zeta series is a summation of 1 by 1 power s plus 1 by 2 power s plus 1 by 3 power s up to infinite terms, where s is a complex number of the form a plus ib, where a and b are real numbers and I is the imaginary number. And this is the definition of the eta series. This is the alternating form of this zeta series. So it has 1 by 1 power s minus 1 by 2 power s plus 1 by 3 power s minus 1 by 4 power s. So this is the alternating sequence. So these things are defined as infinite series. When the real part of s is less than or equal to 0, both these series diverge. And when the real part of s, that is a, is greater than 1, then these both series converge. But in the region where a is between 0 and 1, or the real part of s is between 0 and 1, the zeta series diverges, but the eta series converges. Assuming that this series is convergent, we can write out the zeta series as a difference of these two series, similar to what we did with the harmonic series, alternate series. So eta s can be written as zeta s minus 2 by 2s into zeta s, which in other words, rearranging, we get zeta s is equal to eta s divided by this factor. So this is valid only when zeta s and eta s both are converging. But in the region 0, 1, where zeta s is divergent, we can use this definition as the definition of zeta instead of relying on this infinite series summation definition. So if we redefine, then the zeta function becomes gets convergence in the region 0 to 1. But we know the actual zeta function has a well-defined summation of a different form. So zeta of s comma n is equal to n power 1 minus s by 1 minus plus some residue functions. And this factor n power 1 minus s by 1 minus s gives the actual divergence to this series. So basically, because of the redefinition, the zeta function does not correspond to the infinite series summation in the domain 0 to 1. It is a new function now. And using the new definition, we can say the zeta s is equal to 0 wherever eta s is equal to 0. In fact, we discover that finding the solution s when eta s is 0 depends on the actual divergent form of zeta s. Besides, if we are interested in evaluating the actual number series, we should consider the divergent series as a finite series. Therefore, let us consider the zeta series with finite number of terms n. So we will get an expression like this. So defining it as a finite series, we will have two parameters defining the function s comma n, where s is the power to which each term is raised and n is the number of terms. Let us define, so we can define the eta series as this. So here we have taken up to 2n terms because we want this last term to be negative. So there are even number of terms in the series. So using these above two definitions, we get that eta of 2n terms can be expressed as difference between these two series, these two finite series. So there are 2n terms here and there are n terms here, and adding these two up, we'll get the same series of 2n terms. So from this we can see, in this we'll see that if the real part of s is greater than 0 in the eta series, and if n is very very large, n tending to infinity, then we can drop this n factor and eta is converges. Because eta is converges, we can drop this, and at s equals 0, eta s comma to n is just converts into this series, alternating of summation of alternating ones, 1 minus 1 plus 1 and so on up to 2n terms. Since there are even number of terms here, we get a 0. In general, we can use a geometric series to find the sum of this series for any n, both odd or even. Basically, from the geometric series summation, we know that if this is a geometric series 1 plus r square up to n terms, then the summation is represented as 1 minus r power n divided by 1 minus r, where r is not equal to 1. So if in this series we put r equals minus 1 here, then we get this expression, 1 minus 1 power n divided by 2. So basically this means that n is odd. When n is odd, the sum turns out to be 1, and when n is even, the sum is 0. So no matter how large the number n is, it will always be either odd or even. Therefore s equals 0 is not a solution for the series summation eta s equals 0, because at s equals 0, eta s does not converge. It alternates between the two values 0 and 1. It has a divergent solution here at s equals 1. Sorry, at s equals 0. And when the real part of s is greater than 1 and there is a lot of terms n tending to infinity, then the zeta series also converges. Basically, we can drop n here because zeta of s comma n has the same value of zeta of s comma 2n, and so we'll drop. So if this converges, then we can replace these terms, all the n's here, we can drop all the n's here, and we get this expression, eta s is 1 minus 2 by 2s zeta s, which is the analytic continuation, which is the form we discussed earlier. So this is the redefinition of zeta s to make it continuous in the region 0, 1. But we know from the real zeta series that the zeta function can be approximated by its integral form. Similarly, even the complex zeta series can be approximated by the integral form. So zeta of Sn, which is the summation of this up to n terms, has this form, is very close to the integral of 1 by ks plus some residual term. So what we get is, this is the major term, n power 1 minus s by 1 minus s, and there is a small residue f of s. So using this integral form in the formula relating eta and zeta functions, finite length series, what we get is this. Basically this term drops off. What is left in the eta series is just this term independent of an f of s. So which basically indicates that eta is a convergent series, and we need not use this 2n here. And f of s can be rewritten as difference between the zeta series and the integral form, because that is the formula. Zeta s is just the integral form plus this residue. So the residue can be expressed as this. So this means these are the two factors of the eta series. So eta can be 0 under two circumstances. One, either this is 0 or this part is 0. So when this is 0, what we get is 1 minus 2 by 2s is 0, which means 2 power s minus 1 equals 1. And 1 can be expressed in a complex form as this, e power 2m I pi, where m is an integer. So what we get is s has this form, 1 plus I into 2m pi by natural log 2. These are the zeros of the eta function at when the real part of s is 1. Here note that m cannot be 0, because at s equals 1 eta s is not 0, but it can be any integer, plus 1 minus 1 plus 2 minus 2 and so on. So this is one set of zeros of the eta series. The other set of zeros we get when this portion of this factor of the eta formula is 0. So basically this means eta of Sn is exactly this expression. So the summation of eta series up to n terms is exactly equal to n power 1 minus s by 1 minus s. No residue. The residue is 0 in this. If the residue is 0, then the eta series is 0. This means if we are taking up to n minus 1 terms or n plus 1 terms, we just replace this factor n by that those number of terms. Here n minus 1, so n minus 1 power 1 minus s divided by 1 minus s. So this is a series with n terms. This is a series with n minus 1 terms. If we take a difference between these two, what we end up is, this is the last remaining term. 1 by n power s is the difference between these two summations, and which will be equal to the difference between these two integral forms. So 1 by 1 power s is equal to the difference between these two forms, which basically gives us the equation 1 plus 1 by n power s is equal to 1 plus s by n. So this has obvious solutions as s equals 0 and s equals 1. But in both the cases, s equals 0 and s equals 1, we can verify that eta s is not equal to 0. At s equals 0, eta function is divergent, as we saw earlier. And at s equals 1, basically this form becomes 1 by 0 form, and this is indeterminate. Actually, this whole form this formula does not itself work. We have to use a better formula. So at s equals 1, what still works is the original definition, that original relationship that we found between eta and zeta. This still holds, and using this we can find the eta 1 is natural log of 2, as we did in the earlier part of the presentation. So the real solutions for this equation does not work. So let's consider the complex solution. 1 plus 1 by n, the complex solution s. So s is a complex solution of the form a plus ib. So what we get is this ib, a plus ib term can be replaced with this exponential form, and this is on the right hand side, and this exponential form can be further converted into cos theta plus I sin theta form. So this is what we get on the left hand side. So using this equation, what we find is, by equating the real and the imaginary parts of on the LHS and the RHS, and dividing the imaginary part by the real part, we get this tan term here. This is sine by cos terms. We'll get a tan term here. Tan b log of n plus 1 by n is b by a plus n. As n tends to infinity, this term tends close to 0. So we can approximate this tan function as just whatever is inside theta. So this is very close to this. So we can cancel the b terms. What we will be left with is natural log of 1 plus 1 by n is nearly equal to 1 by a plus n. So from the Maclaurin series expansion, we know that log of 1 plus y is nearly equal to y minus y square by 2 up to second order. So using this approximation here, we get log of 1 plus 1 by n is 1 plus 1 by n minus 1 by 2n square. So which is nearly equal to the series expansion of this up to 2 terms is this 1 by n into 1 minus a by n. So we can see that a should be almost equal to half. So that LHS becomes equal to RHS. So we get a is nearly half from this condition. Zeta of Sn is exactly n power 1 minus s by 1 minus s, which is nothing but the same as this equation. We can also square the real and the imaginary parts, add them up and equate it to the same operation done on the right hand side. So we get that 1 plus 1 by n 2 power a, because cos square plus sin square becomes 1. Those terms cancel off on the left hand side. What will be left with is this term, and on the right hand side we'll be left with the square of this plus the square of this term. So when n tends to infinity, we can drop this term by n square term. So what we'll be left with is this term on the left hand side is almost equal to 1 plus 2a by n. So when a equals half, this left hand side is almost nearly equal to right hand side. Again, from this expression zeta Sn equals n power 1 minus s by 1 minus s, we get a is nearly half. So basically there are two ways of getting a is nearly half from this equation or this equation, and these are the two ways. So in the first way, a is nearly half, what we can see is a is actually slightly less than or equal to 2, and in this we see that a is slightly greater than or equal to 2. So therefore we can say that we find the zeros of this eta series from this condition. From these two conditions we find that a is equal to half. So the zeros of the eta series, note this is not the zeros of the zeta series, the zeros of the eta series we get when a equals half, or when eta series has this integral form summation, when zeta s is exactly equal to this, or when a equals half, we get 0 for the eta series. So possibly we think this Riemann hypothesis is solved here. That is what we expected. This a equals half, we have to prove that the eta series or the zeros are related with the real part of the complex solution S to be half, and this proves a equals half. Possibly we get this. So thank you. Please visit neophysics.com research.html. So in this context we have a challenge. Prove that the zeta series cannot be approximated by the integral form. That is, in this presentation we claim zeta series can be approximated by this integral form. Prove that this is wrong. Prove that it cannot be done. That it cannot be approximated by this integral form, and win $1,000. Offer ends on 31st December 2021. Thank you.